Hey guys, welcome back to the CS Classroom. So what we're going to do today is we're going to talk about topic 5, which is abstract data structures. Now this video is meant to be a review of topic 5. My recommendations for how to approach this topic would be first to not freak out. A lot of students interpret this topic as being extremely difficult, kind of being beyond their capability. But the reality is that once you learn the fundamentals, you can definitely get past it. The level of content seems sophisticated at first, but it's not as difficult to grasp as you think it might be once you start solving problems and actually using them in practice. So the next thing I would also recommend is to practice your reading comprehension. Like, one of the reasons why this topic can be difficult is because a lot of the problems that are involved with it on the IB exam are very, very long and require you to analyze and digest a lot of information just to figure out what the question is asking you and what information you have access to. So we're going to go through some IB problems in this video. Make sure and practice your reading comprehension skills, both when looking at some of these problems in the video, but also when practicing on your own. And finally, this is probably kind of a repetition of like everything I just said, but you need to do practice problems, which is why, again, that's what's going to be in this video. So to conclude, do practice problems. Now, we're going to be talking about two types of data structures. The first one is static data structures. Static data structures are basically arrays. That's the most common static data structure that you see in the IB. Now, what a static data structure means is that the number of elements is determined at the creation of the data structure. So it can't be changed later on. So you might have an array called nums that looks something like this. That means that you have an array called nums with 500 elements, and that cannot be changed. We can't have 501 or we can't have 502. Now, one of the problems with static data structures is that they can be memory inefficient because these 500 elements are allocated in memory as soon as this array is created. So that means that if you don't fill in any of the 500 positions in this array, they just stay empty, and that memory space is being unused for no real reason at all. Now, I would say that the other thing about static data structures is that it can be iterated through using for loops. In fact, with static data structures, one advantage we have over the other type of data structure, which we'll go over, is the fact that in static data structures, you can go forward, you can go backwards using loops, but also you can access individual elements. You can access them directly like this. Versus, as we see next in dynamic data structures, we're not able to do that. So just being able to move through the data structure in multiple directions and directly to elements is a significant advantage of static data structures. Now, dynamic data structures are probably nearly all of the data structures that you will use in topic 5, or rather, I mean, it kind of depends with some of them, but generally collections, which you should have learned about in the SL curriculum, are examples of dynamic data structures. So there's no need to predetermine the number of elements. Any number of elements can exist at any time. We can add elements to dynamic data structures, unlike with arrays. We don't need to pre-allocate we don't need to pre-allocate the size or memory addresses for dynamic data structures. So basically, with a dynamic data structure, each element exists at a particular memory address, which is also true for static data structures. But for static data structures, we tend to have all of our memory located together like this. So all of this, so basically continuous memory addresses. So if you have a memory address of 0, 1, 2, 3, 4, 5, 6, 7, we're looking at a static data structure. Now, with dynamic data structures, we also have particular memory addresses, but these don't have to be located next to each other, unlike in static data structures. And each one of these is called a node. And the node has a pointer to the next element in the data structure, which could actually be anywhere else in the RAM. So for example, if we have a node of a dynamic data structure with some information in position 0 in the RAM, this being position 0, then we might have what's called a pointer to another position in the RAM, maybe right here. And there will be some information there as well. What that means is that when we're iterating through a dynamic data structure, we're going to go to 0. Then next we have a pointer to 4, so we're going to go to 4, and then we're going to go wherever else that particular node at 4 points to. This means that we're more memory efficient than static data structures because we can basically put memory anywhere, and we're not pre-allocating a certain amount of memory next to each other. So we can have memory for the same data structure stored all over our RAM, basically where we want. And there's not really going to be any just empty spaces that are sitting there in this data structure. Now, with dynamic data structures, we can iterate through it using while loops. Again, one of the differences from static data structures is that we can only move forward in a dynamic data structure. We can't move backwards, and we can't access specific elements. So if we have a collection called like nums, we cannot just go access nums 53 like we would in an array. This is not possible. Additionally, right off the bat, we don't necessarily know how many elements are going to be in that collection. So we can iterate through the whole collection, have a counter, and figure it out. But we don't have a predetermined number of elements. So we kind of have to iterate and find out for ourselves. There's no dot length like there might be in a static data structure. That doesn't exist here. So that's the big difference between dynamic data structures and static data structures. I would say that all the data structures we're going to go through in topic 5 are going to be dynamic data structures. There's some caveats to that, but by and large, that's the way that it works. Here is just a table that basically illustrates what we just talked about. I think the only thing missing from this table is the fact that with static versus dynamic, with static we can move forward and backwards. With dynamic we can only move forwards. And with static we can also access specific indices or specific elements in our data structure. So we can just say specific elements. Versus in a dynamic data structure we can't do that. We can iterate through our data structure and try to find that particular element, but we can't go directly to a specific element. And again, an example of a static data structure is an array, and an example of a dynamic data structure is going to be a collection, among many others that we'll find out about today. So what we're going to deal with now is a very static data structure, which is 2D arrays. Now, the typical 1D arrays that we're used to look something like this. So we've got an array and we've got just, a couple of elements like this. 2D arrays are essentially the same thing, except instead of having elements that are integers or floats or strings, we have an array of arrays. So what we're going to have now is we're going to have something like this. Let's say it's 0, 2, 3, that is what a 2D array looks like. Now, 2D arrays are, as we said, arrays of arrays. And if we're representing a 2D array, we're going to represent it in this format. Now, I want to clarify by saying that 2D arrays are typically displayed as a grid. And in general, they are used to display data that can be represented in 2 dimensions. So this is a 2D array. But on the IB exam, and in general, you're most likely to see a 2D array like this. So 0, 2, 3, 5, 4, 6, 7, 8, 9. So that's something you're most likely to see. Now, if we want to go to specific elements on a 2D array, we would write something like this. So let's say this array is equal to nums. Or the name of this array is nums. We wanted to go to nums, or if we were to go to nums 0, 2, sorry, that's not the way you'd write it technically. I'm writing it like a coordinate because it's really in 2D. This is the way it would actually look in pseudocode. If we were to go to nums 0, 2, that would be row 0, column 2. So that means we would be right here. If you were to go to nums 1, 2, that would be row 1, column 2. So this is going to be row 1, 0, 1, 2, and then column 2, which would be this element right here. So that's how we can actually navigate through a 2D array. Now, as I said before, they're used to display data points with 2 dimensions and often grids, and that's the way you're going to see them. And you're going to be working with them in the IB exam and just in general in real life whenever you do use 2D arrays. Now, what we're going to do now is we're going to shift over to Visual Studio and do a little bit of pseudocode coding. And we're going to complete some basic tasks involving 2D arrays. If you watched my part 1 video, it's a very similar concept to what was seen in that video, where these are kind of the basic things you should know how to do. This may not be like exactly, like on the IB exam, you're going to have tasks or some variation of this. But if you understand how these basic tasks function, you should be able to tackle those. So let's go write some code. So let's start with identifying specific positions in 2D arrays. As part of this particular task, what we're going to do is we're actually just going to create a 2D array. We'll call it grades. So this might represent grades for different students. Index 0 could be one student, index 1 could be another student, index 2 could be another student, and so forth. So let's assume that we have 3 students and we have 3 grades for each of them that are being represented in this particular 2D array. Oh man, let's give someone some really bad grades. Okay, not that it makes a difference, but anyways. So notice these are separated by a comma. Again, it's like a regular array, except your elements are arrays themselves. Now, if we wanted to, for example, output this entire row, we could actually just do grades. We could do output grades 0. However, if we wanted to output the last value, or actually, so this one would be grade 0 right here. If we wanted to output this one right here, that'd be grades 1. And that would allow us to output the entire row. Now within this row, if we wanted to output, let's say 94, then we would have grades 1, 2. If we wanted to output 93, it would be 1, 1. If we wanted to output 92, it would be 1, 0, and so forth. So this is basically how we can represent and how we can access individual values in a 2D array using pseudocode. Now our next task is to iterate through 2D arrays. So basically what we're going to use is we're going to use 2 for loops. We're going to have one index that will iterate through each row, and then we'll have another index that will iterate through individual values in the row. So if we're going to do loop I from 0 to grades.length minus 1. And then we're going to do loop j from 0 to grades.length, or grades I dot length minus 1. So what that means is that we're going to go 0, 1, 2, and then each time, so for example, when I equals 0, we're going to go 0, 1, 2. Now, actually, all of these don't have to be the same length. So we could have something like this. We could have more grades for one, or we could have fewer grades for another. But regardless of what that is, the top loop is going to go to each one of these rows. And then each time we go to an individual row, the bottom row is going to get the length of that particular row through grades I dot length. And then we're going to go all the way to the end of that. So basically what you need to know is that we're going to use nested loops. The top loop allows us to go to each row or each individual array element. And then the second loop allows us to iterate through that individual array element. So our task was basically to iterate through 2D arrays, and we're just going to assume that means we want to output every value. So if we do that, what we can do is we can say output I, or we can say output grades I, j, end loop, and then end loop. Okay, so that's how we iterate through a 2D array and just output all of the contents. You're going to always use a nested loop. So next, how do we iterate through just rows in 2D arrays? We kind of just went over that. If we just wanted to print out rows, like if you just wanted to print out this row and then this row and this row, so basically if we wanted to print out 3 arrays, we would just do loop I from 0 to grades.length, or grades.length minus 1. And then we just do output grades I. And what that would basically do is that would just print out this, and then this, and then this, just in sequence. So that's just printing out each individual row. Now this is actually simpler than this one, but it's good to know because maybe some situations in which you need to do something different with each row, or you need to be able to analyze each individual array element in a different way. It's just something that should be considered. Now, iterating through columns in 2D arrays, that's actually kind of a misnomer because iterating through columns means basically this, right? Basically, we're just outputting every single element. We're going to print out, this one would print out 78. Like, for example, this piece of code we just went over would print 78, 89, 89, 94, 92, 31. I would say, let's say, for example, you wanted to output only everything in the first element. So let's say we had these all the same. It was like a perfect grid. And you just wanted to output everything in just position 0 right here. Then what we would do is we would just do loop I from 0 to grades dot length -1. And then we would just output grades I 0. Because all that means is that we're going to go to every single one of these individual array elements and just print out whatever is at position 0. And that's just printing out everything in one column. Now, the last thing we want to do is count values in 2D arrays. And this kind of gets us to calculating averages, maybe calculating the minimum and maximum. I'm not going to go through all the minimum and maximum stuff because literally the same rules apply as a 1D array. It's just you're going to use a nested loop. But I think it's worth going through how to count and just, some of these basic operations that go just beyond iterating. Oh, by the way, right here, I just want to make sure that before we move on, I do end loop. I know I leave that out sometimes, and that's not intentional. It's just that, I'm so used to coding in Python where we don't do stuff like this that sometimes even for me, it's hard to adapt. So I'm going to go ahead and erase all this. And what we're going to do is we're just going to count how many elements are in grades. So this is basically a review. We're going to say loop I from 0 to grades.length -1. And then we're going to have loop J from 0 to grades.length I -1, iterating through each individual array element. And we should just have a count variable up here equals 0. I spelled length wrong right there. And then we're just going to have count. I guess we could even, let's say we wanted to calculate the average. We could have a sum right here, right? And we could have sum equals sum plus grades ij. And then we're going to have count equals count +1 every time we iterate through an individual element. And we're going to end the loop here, end the loop here. And then we might just do sum average equals sum / count, and then output average. So again, I mean, this is really the main piece you need to know right here. The rest functions pretty similar to how it would if we were just using a 2D array. We could say the same thing if we were calculating a maximum or minimum. We could just say, max equals 0. If grades or max equals, rather, I'd probably say the first value in grades. So you'd say max equals grades 0, 0. Rather. So have max be equal to the first value in our 2D array. And then we would say if grades I, j is greater than max, then max is going to become whatever element that's at. So you can say max equals grades I, j. And then we're going to have end if. And we'll just output max at that point. If we wanted to keep track of the indices or what position that maximum is at, we could say pose, I would actually just say pose row equals 0 and pose column equals 0. And then we would just say pose row equals I, and pose call equals j, and that will give us the particular position of that maximum wherever it is in the 2D array. So those are how you can complete some basic tasks with 2D arrays. In reality, it's not that difficult, particularly if you've got a good foundation in how to work with 1D arrays. So right here, what we've got is an IB problem that involves 2D arrays. And it starts out with just a basic problem with methods. So right here we have A, it says, and we have A, and we've got two parts to A, and it says assume A equals 3 and B equals 5. So you've got two parameters for this method called swap, and state the value of A and B after the execution of swap AB. So we're going to have temp equals 3, and then B equals 3, and that is, so temp is going to be equal to 3, and B ends up being equal to 3 as well, and then again A is equal, this is just really weird. So the values of A and B would actually just both be 3. And accordingly, like this isn't a trick, it's just how the algorithm used in method swap would need to be modified to successfully exchange the values of variables A and B. So I'm just going to go ahead and write what the function would look like. If we had swap A and B, and we wanted to exchange the values, so assuming like we'll just say like if we had A equals 3 and B equals 5, we would just want those values to be exchanged. Or really, like, I guess the way that this would work out would just be swap 3, 5, right? So in order for that to be possible, in order to fix any error right here, what we might want to do instead is just have temp equals A equals B, and then B equals temp. And then we can just have n swap, and then both of those values would be swapped. So that should generally be our answer for these two questions. And that's basically what we have right here in the mark scheme. Now right here, we've got a method swap rows that swaps the elements of two rows, so row K and row L, in the two-dimensional array mat. So for example, right here we have row 1 and we have row 4, and we can swap rows. So we have one parameter as the actual array, which in this case is mat, and we can swap rows 1 and 4. So now array 1 has what is in array 4. So basically, the array at index 1 is the same as what was at index 4, and vice versa. So right here it says use pseudocode to construct an algorithm for the method swap rows. So I'm going to go ahead and just say swap rows mat K and then L, where K is kind of going to be our first row, and okay, that's what it's going to look like, and L is going to be the second row. Okay, so let's go ahead and just like actually construct a little array, right? So let's say we've got that. So what we want to do basically, and let's just say mat equals that. Now this is just an example, so we can work with it pretty easily here in the code. So basically the idea is we'd want, if we put 0 and 2, it's okay if we had mat, if we had swap row, mat 0 and then 2. We could actually just exchange those, these different rows. So I would say like the way that I would do this is I'd probably create a new, I guess one way we could do it, we could actually just create a new array. Or what we could do, so if you go right here, it says use pseudocode to construct an algorithm for the method swap rows. In this question, actually, there are a couple of ways to do it. I actually assume that you could use the swap function, but even so, if not, what we can do is we can just go through the index for each of these, and then we can just kind of swap those rows. So basically what that means is that what we're going to do is we're going to say for loop from 0 to let's say mat k dot length. Okay, these should all have, generally you're going to have, when you have 2D arrays in the IB, they're all going to have all of the individual array elements are going to have the same length, but whatever. So that means we're going to go from 0, 1, 2. Okay. And basically what I want to do is I want to say for each of those, we're going to have temp equals mat k. Or I'm going to say loop I, rather, from 0 to mat k. So we're going to say temp equals mat k I. And then we'll say mat j, so mat l I equals the temp. Is that what we want to do? She will say, we've got temp right there. Actually, I think I want to say mat ki equals mat li. And then once we've transferred that over, you can say mat li equals temp. So that's actually probably how we could do that. So basically what we're doing is we're iterating through this one right here, and for each element, we are swapping whatever is in row K with whatever is in row L, this way. And we're going to the first element here, swapping them, going to the second element here, swapping them, going to the third element here, and then just swapping them. And I'm pretty sure that's what, that's basically what the mark scheme says. So it's a good example of how to work with 2D arrays. Actually, in this one, we only needed to use one loop, and we were just kind of working with one row and then swapping that with another row. Okay, what we're going to do next is we're going to talk briefly about recursion. So recursion is basically like this example right here, when we write a function and we call the function itself inside the function. So right here, this is part of the function, but we're making a function call right here. So that's basically what recursion is. Now, with recursion, like generally we're using recursion situations where the next result of an operation depends on the current result. Some good examples include the Fibonacci sequence or a factorial function. Factorial function looks like this, so we might have 4 factorial equals 4 times 3 times 2 times 1. That means we're going to multiply 2 times 1, and then 3 times 2 equals 6, and then 4 times the result of that, which would give us 24. That's an example of when we would use recursion. Now we have 2 terms right here. We have a base case, and we have a recursive step. If you look right here, this right here is going to be our base case. And this right here is going to be our recursive step. So basically our base case is what it takes for the whole recursive process to end. So right here, for example, if we input 3 right here, okay, we're going to have return 3 times fac 2. Okay. And then we're going to put 2 in here, right, for this part right here. So then we're going to have 2, we're going to check, is 2 equal to 1? No. So we're going to return 2 times fac 1. I will say fac 1. Okay. And now we got fac 1, we're going to put 1 in here, and we're going to say if n equals 1, then return n, which means that we're actually going to return 1 this time, because our input is just 1. So fac 1 is 1. So this is going to give us 2 right here. 2 times 1. So that means that then this return statement corresponds to fac 2, which means fac 2 is just going to be equal to 2. And fac 3 ultimately asks us to return 3 times fac 2. So fac 2 is going to be 2. Then our output is going to be 6. Now notice we stopped right here when we actually had a whole number instead of another return statement with our function in it. And we stopped there because n was equal to 1. Now that's why n can be considered our base case. That's the lowest parameter that we go down to. And we're just going to return a value rather than another function call. And then work our way back up from there to what we actually want, which was fac 3 or 3 times fac 2, which just equals 6. So this is like a basic example of recursion. Now on the IB exam, the thing is what I want to do right here is I want to cover like the very basic tasks that you need to do for recursion. Now on the IB exam, you may see recursive functions, and generally you're only going to have to either understand how they work or calculate the output of a recursive function. Now, there are situations in which you may see recursive code, but you're never going to have to actually write a recursive solution. Like there may be questions that say you can use recursion, but that doesn't mean you have to. Moreover, to actually teach how to like detect and write recursion would be a much longer tutorial than this. So I'm just going to focus on like really like basically what you're going to see on the IB, and we're going to look at some recursion related IB functions. Okay, so right here it says consider the following recursive algorithm fun x9 where x and n are two integers. The return statement gives the value that the algorithm generates. Determine how many times multiplication is performed when this algorithm is executed. So in this whole function right here, we are just performing multiplication right here. So that means however many times we hit this line of code, that's going to be the number of times that multiplication is performed. So let's say, for example, I actually want to start. So the next question is going to be fun 2, 3, and we need to find the value. So we can use that to kind of like work with this and see how many times we're going to have to do multiplication. So if we have fun 2, 3, the first time we're going to return 2 times fun 2, 2. Then we're going to return 2 times fun 2, 1, because we had a parameter of 2 then. And then we're going to return 2 times fun 2, 0. And we're going to do that. We're just going to stop right there because we're going to have a parameter of 0 for n. And right here we can see if n is less than or equal to 0, we just return 1. So that means that if we have right here, so right here we had an n of 3, okay? And we saw that every time we were just subtracting 1 from that value until we got to 0. So that means that basically we had 2, 1, 0. So similarly, if we had a n of 4, so each one of these times we had to do multiplication. We had to do multiplication 3 times. So looking at the sequence, that also means if we had a value, if we had fun x4 or fun 2, 4, we would have had to multiply 4 times. If we had fun 2, 5, we would have had to multiply 5 times. So just by working this out and looking at this value right here, we can tell that the number of times that multiplication is performed is going to be n. Now, in kind of gaming this problem out, or kind of tracing this problem actually, what we can also do is we can determine the value of fun 2, 3. Now, right here we know that if our n is 0, then we're going to return 1 right here. So that means we're going to have 2 times 1 equals 2. So that means that fun 2, 1, for which this was the return statement, is going to be equal to 2. So that means that in this return statement right here, we're going to have fun 2, 1 is 2. So that means that fun 2, 2, or sorry, I should put that right there, fun 2, 1. It's maybe not that clear, but that means that fun 2, 2 is going to equal to 4, because you got 2 times 2 right here. And then we still have this return statement right here. So we're going to do 2 times fun 2, 2. So that means that fun 2, 3 is going to equal 8. Okay. So the value of fun 2, 3 is just 8. Now let's take the purpose of this recursive algorithm. So notice how we went 2, 4, 8, right? If we had like fun 3, 2, for example, okay, that would have been 3 times 1, 3 times 2, or 3 times 3, and then 3 times 9. If we had 4, 3, that would have been like 4 times 1, 4 times 2, and then 4 times 3. So the purpose of this algorithm is really to calculate x of n, to calculate an exponential, to calculate x to the power of n. So some sort of exponential value when there are two integers. Now that we've now you have a basic idea how recursion is, and we've seen some problems, we're going to look at some of the pros and cons of recursion. So the pro of recursion is that the code is cleaner and more elegant, which it's just a simpler way to solve problems. Complex tasks can be broken down into a repetitive series of similar subproblems. Basically, it's just a lot simpler to visualize or to work with when we're trying to solve certain types of problems that have a lot of other subproblems that need to be solved. And sequence generation is much easier than with nested loops. So it's easier for us to make calculations, like for example, the factorial that we looked at. Disadvantages is that recursion is just hard. Sometimes recursive logic can be difficult to follow. Additionally, it's usually more inefficient because every time we make a function call, we're taking up memory. So that can add up really quickly. And partly because recursive logic is hard to follow, it can be harder to debug recursive functions. Now again, I want to emphasize that in order for you to fully understand recursion, you need to write some recursive code and solve some recursive problems. This is just kind of a basic review of what you'll see in the IB. That being said, you don't really need to learn how to write recursive code. It might help you understand it, but you don't really need to learn how to solve problems using recursion, because any problems in the IB will give you the option of either using recursion or iteration to solve the problem. So understanding how recursion works is kind of the most basic thing you need to be able to do on the IB. And frankly, as I said before, if I have to completely reteach recursion, that would probably take a lot longer than you'd want to watch this video for. Anyways, that's the end of part 1. Part 2, we're going to cover stacks and queues, binary trees, and linked lists. If you are currently preparing for the IB, SL, or HL exam, please be sure to check out the link in the description, which contains links to study guides for both SL and HL paper 1, as well as HL paper 3 with some sample practice questions and answers. Moreover, if you found value in this video, please remember to like and subscribe to the channel. Have a nice day.